Okay, folks, so let's talk about catabolism of this acyl-CoA. Recall in catabolism, we're breaking down larger molecules into smaller molecules, generally oxidizing them along the way. But if you think of the lipid tail, right, we have a mostly saturated structure with a lot of carbon-carbon-carbon-hydrogen bonds. Those are kind of difficult to break apart. We've certainly seen that in glycolysis and the citric acid cycle. That's definitely true here for lipid metabolism. We have to find a creative way to break these carbon-carbon bonds. So in comes beta oxidation. We have a series of 4 steps that basically repeat over and over in order to eventually chop off units of acetyl-CoA. The summary of this pathway is on the right. We have all those structures, but don't worry, we'll go through this more slowly. Generally, the 4 steps are this. First, we form a trans double bond. We're going to hydrate or add water across that double bond. We're going to oxidize a hydroxyl to a carbonyl. Now that we've created that fantastic electrophile, we're going to use it to cleave off 2 carbons as acetyl-CoA. So let's go into a bit more detail and walk a bit more slowly through this. Step 1, acyl-CoA dehydrogenase oxidizes our acyl chain and forms a trans double bond. Comparing the top structure to the bottom structure, you can probably see this. It's thought that in the mechanism, we have a base that does the proton abstraction. Here's going to be a glutamate. It's difficult to see in this, picture, I know, but our glutamate's up here. Then it's thought that we have transfer of a hydride to FAD. I know we discussed earlier that FAD does transfers really of a hydrogen radical. This is just the hypothesized mechanism. So all in all, removing 2 protons, 2 electrons across the bond, oxidizing to this trans double bond. In the process, we've made FADH2, and this is happening in the mitochondria now. So the FADH2 can go head on to the electron transport chain, move its electrons through, move some protons across the membrane, helping to create ATP. After we've formed that double bond, folks, this metabolite moves on to an enzyme complex that will perform steps 2 through 4. This enzyme complex contains all 3 enzymes that will perform the rest of the steps. So what's happening here? Well, we enter with this trans double bond. In the first step, our hydratase is going to hydrate or add water across the double bond. Following that, a dehydrogenase is going to oxidize the hydroxyl to carbonyl. In the process, we've made an NADH. Finally, we have something that looks like a fantastic electrophile. So a thiolase will help break apart our acyl chain, removing 2 carbons as acetyl-CoA, leaving us with an acyl chain that's 2 carbons shorter. There's one thing that I do want to mention about this enzyme complex. There are really 3 different versions of the complex. Recall that enzyme active sites tend to complement their substrates. So if this substrate starts off quite long, but is getting shorter and shorter, at some point the substrate will not fit very tightly within the active site. So there's a version of this 3 enzyme complex that binds longer chain, medium acyl chains, or shorter chains. But they all perform these same 3 steps.